Hello everyone, my name is Sofía Jimena Avilés Amador, and today I will present our work titled Impact of NAFION Content in Ruthenium Oxide Catalytic Inks Towards the Oxygen Evolution Reaction. This research focuses on improving the performance of proton exchange membrane, or PM electrolyzers for green hydrogen production by optimizing the composition of catalytic inks used at the anode. As you know, water electrolysis is one of the cleanest ways to produce hydrogen. In PM electrolyzers, the oxygen evolution reaction, or OER, happens at the anodes. However, this reaction has slow kinetic, which means we need highly active and stable catalysts to make it more efficient. Ruthenium oxide is one of the most promising catalysts in acidic media because of its high activity. One key component in these inks is NAFION, an ionomer that improves proton conductivity, but its amount can also affect catalyst dispersion and block active sites. Our goal was to find the optimal NAFION content for ruthenium oxide-based inks and test their performance in a PM electrolyzer. The main objective of this study was to evaluate the effect of different NAFION contents in ruthenium oxide inks and determine the best application method for membrane electrode assemblies to maximize electrochemical performance. We used commercial ruthenium oxide dispersed in an isopropanol water mixture with NAFION added in a different weight percentage, 0.1%, 0.4%, 1%, 4%, and 40%. The inks were homogenized by sonication to ensure uniform dispersion. We tested each ink in sulfuric acid electrolyte using a glassy carbon working electrode, a platinum mesh counter electrode, and a hydrogen bubble reference electrode. We performed cyclic voltammetry from 0 to 1.5 volts at 50 millivolts per second, linear sweep voltammetry from 1.24 to 1.68 volts at 5 millivolts per second, and finally electrochemical impedance spectroscopy from 10 kHz to 1 Hz at 1.8 volts. For the electrolyzer test, we used NAFION 115 membranes and coated the anode with the optimal ink via manual airbrushing. The cathode was a platinum carbon catalyst layer. Membrane electrode assemblies were hot pressed at 80 degrees Celsius and 150 bar, then tested at different temperatures for 25, 60, and 80 degrees Celsius, and flow rates for 24.5, 72.5, and 123.4 milliliters per minute. Cyclic voltammetry results showed that the 0.4% NAFION ink reached the highest current density among the samples. Higher NAFION loadings like 4 and 40% reduced performance due to activity site blockage. Linear swap voltammetry showed that 0.4% NAFION initiated OER at 1.42 volts, slightly earlier than the 1% NAFION ink. However, the 1% ink achieved the highest current density once the reaction started. TAFL analysis indicate that the 1% NAFION ink had the lowest slope, 62 millivolts per decade, suggesting faster electron transfer kinetic. The 0.4% NAFION ink had a slope of 139 millivolts per decade. Finally, the electrochemical impedance spectroscopy showed that the 0.4% NAFION had the lowest ohmic resistance. The 0.4% NAFION ink was chosen for membrane electrode assembly fabrication. Best preliminary performance was observed at 72.5 milliliters per minute at 80 degrees Celsius. The study is also identified 1% NAFION as a promising alternative, and both will be analyzed further for long-term stability. In summary, NAFION contains and strongly affects both the ionic conductivity and accessibility of active sites in ruthenium oxide-based inks. 0.4% NAFION offered the lowest resistance and strong overall performance, making it the optimal formulation for membrane electrode assembly preparation in our study. 1% NAFION showed better electron transfer kinetic, so it remains a viable candidate. Further work will include chronoamperometry and extended cycling to test long-term stability and durability. By optimizing NAFION content and application techniques, we can improve the efficiency of PM electrolyzers, making green hydrogen production more cost-effective and sustainable.